Okay, so for our second talk of the afternoon, it's a great pleasure to introduce Melissa Liu, who will talk about wall crossing for the mirror quintic.
First of all, I wish to thank the organizers for the opportunity to speak at this conference. Today, I will talk about wall crossing for the mirror quintic. This is based on joint work in progress with my colleague, Konstantin Alashkin. Oh, can you all hear me well?
Perfect. Reasonably well, yeah.
Thank you. Yeah, so of course, like everybody's familiar with like Quintic. So I just want to fix the notation. So in this talk, we will let W0x denote the Fermat quintic polynomial in 5 variables. And x is the Fermat quintic Calabi-Yau threefold defined by the zero locus of this W0 in P4. Mu5 will denote the group of fifth roots of unity, and G0 is this finite abelian group, which is isomorphic to mu5 to the 4th power. In this talk, the mirror quintic is the Calabi-Yau 3 orbifold obtained by quotient x by the action of G bar on P4. So where G bar is the quotient of G0 by the diagonal subgroup, which acts trivially on P4. And this action preserves the hypersurface. So we will, so this will be the mirror quintic, so we don't resolve this. It is a Calabi-Yau, compact Calabi-Yau 3 orbifold. And it and x, so we call it x check, and x check and x are mirror pair, at least in this sense, in terms of Hodge numbers. So for this quintic polynomial, we will consider four theories. So the first theory is the Calabi-Yau threefold X, the quintic Calabi-Yau threefold X. We will consider the Gromov-Witten theory of the quintic Calabi-Yau threefold. The second theory is Calabi-Yau 3 orbifold, the quintic mirror quintic, and we will consider the orbifold Gromov-Witten theory of the mirror quintic. And the third theory is the A model topological string on the lambda Ginsburg model, C5 mod out the action of mu5 diagonally with the superpotential the Fermat quintic polynomial. And the mathematical theory of this is given by Van Jarvis-Witten theory. These are virtual counts of solutions to the Witten's equation associated to the Fermat quintic polynomial. And the last example is quotient by a larger group G0, defined in the previous page. In each of these theories, there is a state space. The state space is a graded complex vector space. We will actually only consider the even part. And so in each of this, so it has a symmetry non-degenerate pairing. And H0 and H6 are due to each other. Under the pairing and dimensions 1 and H2 and H4 are due to each other. So the dimension of HA is 2 times the dimension of H2. And let Z be a formal complex variable with degree Z equal to 2. So we modify this. So now this becomes homogeneous of degree 2. And we define this using the residue and the symmetric pairing so that it becomes a skew symmetry non-degenerate pairing. So for each of the theory, there's a small j function. So here we would like to view this as HAZ valued function depending on T in H2. So these are defined in each of the theory in terms of genus zero descendant invariance. If we choose E1 to E kappa to be a basis of H2 and the upper one to E kappa to be a dual basis of H4, we can write T, expand T in terms of this particular basis, then T1 to, typo T kappa. So these are classified Taylor parameters. Of course, there are some convergence issues, but let's just assume that, so when we don't have convergence issue, so for each T, so it's take its vector valued function. And because in the Calabi-Yau dimension 3 case, yeah, there's you can only insert one descendant to get non-vanishing invariance. So the J function is actually of this form. So we can see that actually, so the F0, which is a generating function of genus zero primary invariance, can be extracted from the J function. And also the small quantum product is commutative and associative with unity 1 in H0, and it's determined by the third partial derivative of this H0. So now in this series, there are I functions and the genus zero mirror theorem in terms of this J function. The small I function is always explicit HAZ valued function depending on certain variable Q1 to Q kappa, the same number as the Taylor parameters. And it can be expanded in terms of, if we expand it in terms of the same basis, then these coefficients are explicit series. In particular, the there's a, so H, it should be H I upper 0 Q is analytic in open neighborhood of 0. And the given style mirror theorem in all these theories takes the following form. So JT0 is equal to IQZ quotient by I upper 0 Q under the mirror map T upper L, which is given by the quotient of ILQ by I0Q. So let me just recall some relevant previous results. So this is the most classical case. If we consider the Gromov-Witten theory on the Quintic Calabi-Yau threefold, and we consider given part is 4-dimensional, H is the restriction of the hyperplane class. And the genus zero mirror conjecture was first proved by Giventhal and Leonid Yao. There has been, there are alternative proofs. I would just like to mention one, which is via quasi maps. Quantum and Ben-Zvi proof apps. So using the theory of stable quasi maps developed jointly with Vash Molly. So this quasi map theory is defined for certain GIP quotients of affine variety by a reductive Lie group. So using this, one can change the moduli space by stability condition by allowing certain points of the domain curve to go into the non-stable locus. And then we have different epsilon correspond to different moduli spaces and defines different J function depending on this epsilon stability condition epsilon. And then they can interpret this version of Merrill theorem I is equal to J as epsilon wall crossing, where the J function defined in this case by stable maps to X correspond to epsilon goes to plus infinity, and the I function corresponds to epsilon goes to 0 plus. So next, so for the mirror quintic, one can consider orbifold Gromov-Witten invariance, and the state space will be, so we will take the state space, we will take the even part of the Chen-Ran cohomology. Now it is much larger, it's 204 dimensional. So Lie and Shoemaker proved the Merrill theorem, like the form I is equal to J. When so this should recall that the I function, J function in this case should takes value in a vector space of dimension 204 and depends on 101 variables. So the Lie and Shoemaker proved the case where one restricts this to the one-dimensional subspace coming from the untwisted sector. And the general case follows from a Quartz-Corti-Zeng's result or Chilton-Fontanelli and Kim's orbifold quasi-map theory. So we consider the third theory, which is the FJRW theory on C5 mod mu5 with superpotential W0. So here the state space is, we take the relative Chen-Ran cohomology and we take the even part, which is 4-dimensional. And in this case, Kyoto-Ran proved a Merrill theorem. And also, it can also be interpreted as epsilon wall crossing. And also, Kyoto-Ran proved the Landau-Ginzburg Flabial correspondence for the quintic. So it can be formulated in the following way. So one already know how to relate J and I for the Merrill for the this Landau-Ginzburg model, and also for the quintic threefold. And then so they show that the I functions in these two theories are related by analytic continuation and syncretic transformation of these two spaces. The FJRW, so finally the FJRW invariant when one quotient by this much larger group G0. In this case, the state space is the even part of the Chen-Ran cohomology. And now it's 204 dimensional. In this case, Pritis and Shoemaker prove a Merrill theorem for this case, and they also proved the Landau-Ginzburg-Calabi-Yau correspondence, but they proved this correspondence. So when one restricts the complexified scalar parameters to a one-dimensional subspace. And it's a similar statement. So these I functions are related by analytic continuation and symplectic transformation. So in this talk, my goal is to explain that how we generalize previous and Shoemaker's results in two directions. So the first, we want to consider the whole 101 dimensional scalar complexified extended scalar parameters. And secondly, so we consider the chamber corresponding to this Landau-Ginzburg model. And next to this chamber, so there are 101 other phases. And one of these phases is the Miro-Quintic phase. And we also want to consider the other 100 phases. And then to understand this, we want to consider this as wall crossing of a theta variable in the gauge linear sigma model. So let me just briefly review the setup. Following the work of Jardim and Beverl and Kim. So the input data of a gauge linear sigma model consists of 5 things. V is a finite dimensional complex vector space. And so G is a subgroup, a reductive algebraic group, and it's a subgroup of GLV. So there's an R symmetry. Oh, so this CR star is just C star. And this is X linearly and faithfully on V. So we may view it as a subgroup of GLV. We assume that we have this G, and we assume that intersection of this C star R with G is a finite subgroup following from Jarvis run, and the C star action commutes with the G action. The finite group must be cyclic generated by some element. J of finite order R, and the surjective group homomorphism is a degree R covering map. So we let gamma be the subgroup of GLV generated by this group and C star R. Then we have a short exact sequence. The quotient is G C star omega. So the gamma action V induces a C star omega action on the smooth arcing stack V quotient by G. So these are the R charges. So this so C star R actually has an honest action on V. So it's CIR integers, but C star omega. So this C star R is an R cover. C star omega, I think in the physics literature, the R charge is like a double cover of this C star omega. So we have V and G and this R charge, and there's a superpotential W, which is a G invariant regular function on this vector space V of degree R with respect to the C star action on V, and descends to a function little w on the quotient stack. of degree 1 with respect to C star omega. So finally, there's a stability condition. So this stability condition gives us a GIT quotient. So so the straight x theta is the GIT quotient, and the curly x theta is the static quotient. And it is assumed that the critical locus of the superpotential is proper in so we say theta is in a geometric phase if V theta is a smooth orbifold. In this talk, we consider abelian gauge linear sigma model. So in our case, G is actually abelian, and this quotient curly x theta is a toric orbifold, and it can be defined in terms of static fan. All right, so I'm going to switch. Okay, so in our case, so now this is a very general setup of the gauge linear sigma model, but we will consider very special case. So the first example is the quintic. So in this example, we will consider G is equal to C star, and V is C6, but the C6 is, has coordinate x1 to x5p, and the action is by so in this case, this is one-dimensional. So when theta is greater than 0, then V so this is KP4, and when theta is less than 0, so this is C5 mod mu5, and in this case, when theta is greater than 0, x theta is KP4, and theta is less than 0, x theta is the quotient. And in this case, the R charge is 0, 0, 0, 0, 0, 2. And so the superpotential is P. And when theta is greater than 0, the critical point so this is exactly our is exactly equal to the Quintic clubial threefold. And in this case, so the GLSM theory for theta is greater 0 is equal to the Gromov-Witten theory of the Quintic threefold. And the GLSM theory for theta less than 0, this is the FJRW theory of C5 mod mu5 with superpotential W0 since P is non-zero here. So we see that the Landau-Ginzburg clubial correspondence is can be viewed as theta wall crossing. So for the wall crossing for the mirror quintic, so today we will consider theta wall crossing. We will not address the epsilon wall crossing. So now let's try to form a gauge linear sigma model for the mirror quintic. So the mirror quintic is so we consider the Landau-Ginzburg model associated to the mirror quintic. So we have this G0 defined before. And then, so we want to consider we want to rewrite, we want to do the following. So we write in the X, in the, so where V is it's 106 dimensional. And the stable part is C5 times C star S. So now this V0 is actually oh, sorry. So V0 will simply show Fourier variety defined by a cone spanned by E1 up to E5. So we consider, so this is we consider a larger lattice. And then defining so this quotient is we take the lattice and we sigma 0 is like consists of all subcones of sigma generated by V1 up to V5. So now we can consider a extended Specchi band. And sigma 0 beta is equal to V1, V5, V6 up to V. So this 101 vectors correspond exactly to the 101 dimensional twisted sector of H2. So we introduce variables SI, AI, where A is from 1 to 101 and I is from 1 to 5, such that 5 plus A is so then we consider the following 101 faces. So they will correspond to blowing up by adding the ray B by plus A. So result of generality, we may order, because this whole thing is a symmetry under the permutation of the 5 coordinate. So without loss of generality, we only need to consider the case sorry, this is actually exactly 5. So without loss of generality, we may consider the following cases. So this is phase 1 to 20, and we call them HA, from 1 to 20. So they are, so up to permutation, this corresponds to 0, 0, 0, 2, 3. And secondly, phase 21 to 50 correspond to 0, 0, 1, 1, 3. And third case, phase 51 and phase 81 to 100 is 1, 1, 1, 2. And finally, phase 101, 1, 1, 1, 1, 1. So this is the case which corresponds to KP4 quotient by the G. And also we have the superpotential is given by but in this, so YA is equal to, for each phase, V theta A. We can also view it as a YA tilde now quotient by some finite group GA bar. So this GA bar is a finite abelian group. So let me, so maybe it will be easier to look at YA tilde. And we look at the 5 representative cases. So each YA is and WA. So in terms of the 6 coordinate, so we see that the other faces are actually not geometric, and it's also not a standard hybrid model. So now for each face, so we have the gauge linear sigma dose stays space. So H, Y, A, W, A. And we take the even parcels 204. So then now we have from case theory of the metric factorization of so given that, so we have certain chain character map. So what we can show is the following. So this is certain like gamma modified I function. So it takes value in the state space. This is equal to the disk partition function applied to beta. So I should say that for each phase, so the left-hand side should be seen as Higgs, and the right-hand side is Coulomb branch. So this is a Higgs-Coulomb duality. So where this partition function so we follow so if theta is in certain phase, then there's a contour depending on the phase. So actually this beta is the so it lived to the matrix factorization of the GOSM. The second, so then this will gives us all the components of the I function in all phases. So the analytic continuation is given by the following. So we have so let's do it in this way. So we consider the Y0, W0. And let's call the left-hand side VB. Oh, sorry.
Melissa?
Oh, yes.
Yeah, I just want to draw your attention to the time.
Oh, yeah, sorry. Yes. So this is so this is the this is the span by, so this is span by components of the I function, and then the analytic continuation is, so we compute like explicitly the great restriction rule, and it turns out it's actually consistent with the Fourier-Mukai transform. So this gives us the theta word crossing. And in particular, so y0 to y101 gives us the 101 dimensional extension of Friedrich and Shoemaker. Oh, thank you for your attention.
Thank you very much, Vincent. Are there questions? You can just unmute yourself and ask. Or raise your hand. Okay, so let's thank the speaker again, and we will reconvene on the hour. Thank you.